Welcome to Model 18, Run Analysis and Equipment Level. So in this model, we're starting to demonstrate case studies. The first case study concerning the run modeling. The further model we are demonstrating as well run analysis budgeting system level. So we are intending to put a system level such as a bogey or break and pantograph system, and then we demonstrate how to model that. But we start with equipment level. It's very important to understand when you model something, some run analysis also for equipment level. The idea is, if it's possible, if you have enough information, to go to components level, and then when you go to component level, we input the reliability, maintainability information, as well as the inspection, preventive maintenance, and associated costs. So usually this level of analysis are kind of analysis that is carried out by vendors. You see that as long as you have all the information, do not take too much time to carry out this analysis and get the conclusion. The most important thing is to check if your target is achieved based on the warranty terms defined in the contract, as well as if it's necessary during design some modification. Okay, we start with a simple example in equipment level, then the next model we jump to system level. So same concept that we have so far, but it's good to just to highlight what you are going to present here. Basically, the run analysis has as a performance index operational availability. Operational availability is uptime divided for the total time. The production efficiency is total production for nominal time. In the case of railway industry, we do not have this performance index, but of course reliability, the chance of equipment operated under defined operation condition until a specific period of time. So in a warranty, we define this time 2 years, 3 years, or even in kilometers, that we do not expect to have failures. Okay, reliability index, the percentage of subsystem or equipment reliability impact on system reliability. So other index that we can use. Failure critical index, percentage of equipment or component of system total failures. So if the system have 10 failures and one specific motor have, in the case of a driver motor, a rotor that's installed in the bogey to start the movement, to provide the movement for the bogey, we have the starter. For example, if you have 10 failures and 5 of them are related to the starter, so the failure critical index for starter is 50%. We also have down event critical index, the percentage of equipment or components number of system shutdowns. So if we have 10 shutdowns and the gearbox is responsible for 7 of such shutdowns, so the down event critical index is 70% for the gearbox. Okay, and downtime critical index is related to time of shutdown. Okay, sometimes you have equipment that have more number of downtime. They are responsible to the highest number of downtime, percentage of number of downtime for a system. But when you look on the downtime unavailability, that's not can be other equipment because of the repair time related for each one equipment. So each one components have different repair time. Usually the accessibility time will be the same, and also to open, but in some cases you need to disassemble the whole equipment to change one component, or it's just open the equipment, you can remove some components. So that's the variation, cause all variation in replace. And if in case of repair time, of course, definitely you have more difference, and then that's different can cause difference in the performance in this downtime critical index and doing event critical index. And we have also in case of production loss index, but it's not in the case of for railways. So let's go move on. We just remember that to carry out a run analysis also in equipment level, need to define the scope Here our scope will be the motor in a bogie, and we need to carry out lifetime data analysis. In this example, we already have input the data, we already have all the PDF parameters for each equipment. It's important to understand that depends how your database is organized, is that will enable you to also to model your system. So that means if your database, if you have a FRACA system that's defined failures in equipment and components level, you'll be able to carry out lifetime data analysis in equipment and components level, and then your RBD that gets the such input will be in this level. By the other hand, if you have a FRACA system where you've got the basis information from the FMEA, such as failure modes, detection, consequence. So if you have clearly the failure modes, you can organize your RBD you can carry out lifetime data analysis in failure mode level, and then you can also organize your RBD in failure mode level. Okay, so it's important to consider that, of course, depends on the time that you are assessing your equipment. It's not all the components that will fail in this period of time, as well as it's not all the failure modes that will happen in this period of time. Mostly to see all the failure modes and have enough data to model a PDF for failure modes, you need to run the equipment for the whole life cycle. And of course, the most critical equipment will always shows up with some failures in component level, in some cases in different failure modes, but not all. We need to be sure to be aware about that. But even though it's good when you organize our FRACA data to collect as much as possible information, detailed information we can. Okay. And then of course we'll go to step 3. We'll model in our RBD. That will be a simple example. We start from component cases in here, applying railway industry case, and then we go to system level, and then we run the simulation, and we will get the critical analysis. So that's the 5 E step. We will not carry out any sensitivity analysis in this example in here, and of course after that we can make, that's the type of presentation that we can have in the conclusion, and then prepare a report. We already saw that in the beginning of this training. So let's go on. Just remember the RBD, we have our diagram blocks, and we can have combinations of series and parallel, or even only blocks in series. So with each equipment cause direct impact in case of failure in the system, or when we go, in this case here we are modeling equipment in a components level. So if a components failed cause direct impact in equipment, such components will be modeled in series. Okay, if you have some combination or redundant components, you have parallel configuration. So our case in here will be the traction motor, very important equipment for railway industry, for the trains and locomotive. What we have in the trains is we have driving motor, traction motor in each wheel axle. So we can, in some cases, many cases, we can run with only one traction motor. But even though we need to be sure about the reliability of the traction motor, in some cases, if it's not well designed, if you have some problems in early life phase, that will cost a lot of money and also impact directly in trains and availability. So here we can see different components that we can have in traction. So we consider the components that can trigger a direct impact in the traction motor, and then such traction motor fail and cause direct impact. Remember that in the very beginning we discussed about failure class. And when you go into a component level, even when we work in equipment or system level, we need to take into account which kind of class of failure we are taking into account to build our RBD. So in this case here we consider failure class A, because that will cause the train shutdown. So all critical equipment in case of failure that will shut down the motors and will cause effect directly in the train. So those failures need to be repaired and replaced as soon. So let's take a look on the traction motor concerning the RBD model. So we are considering these 6 elements here: the traction motor bearing, the traction stator, the rotor, the gear coupling, the gearbox, and the reaction rods. So basically we have the stator that has no maintenance and inspection policy, is electric equipment, so we have run a failure. We did not put any preventive maintenance in this equipment. All others equipment such as rotor, gear coupling, gearbox, reaction rod, traction motor have some inspection and preventive maintenance, and then we can see the impact that we have in the traction motor. So what we expect whenever we implement such inspection and preventive maintenance is that the downtime will be lower than if we do not expect, as well as the impact of the failure in the equipment. So let's take a look further, and then we understand. So here is the simulation of the reliability diagram block. Of course, to run the simulation, we need to first input all reliability, maintainability, and inspection in each one of this block, and then after we run the simulation, we can get the first result, that are the performance. So here we have the operation availability very high, 99.97%. And the operation availability without preventive maintenance, and here we can see that's even higher. That means if we take it out, the preventive maintenance, the reliability is almost 100%. We have the point availability is 100%, the chance that system is available in this time, and the reliability of the equipment, of course, is very high. So that shows the effect of the preventive maintenance, but we need to remind that we have the stator, that's electrical equipment, that have random failure here, and then we have no scheduled maintenance planning for such equipment. That's why there is some impact of such equipment reliability, the degradation in the traction motor, of course. So even though the expected number of failure is very low for this period of time. And then we have other index here. The mean time between failure, mean time between events, mean time to the first failure. As we already discussed before, that's not a good index. As long as I have reliability, expected number of failures, and operation availability, it's not necessary to use this mean time between failure. Mean time is an average, and of course we need to look on each equipment components, PDF, reliability, in order to understand the pattern of the failure, as well as when we have increasing failure rates, in order to input some scheduled maintenance, non-destructive test or inspection to avoid the failures. And that we already discussed, and that's why reliability and expected number of failure and operation availability will be better. In addition, we know that depends on the PDF. If you have a gumbo, for example, that is skewed to the left, if you have if you apply MTTFS index as a reference to implement some preventive maintenance, probably we'll do some preventive maintenance or too late or early than necessary. And if it's earlier than necessary, you do not detect any failure, and if it's later on, the failure will happen before you prevent the failure. So, and by the other way around, if we have a normal PDF, if you consider mean time between failure, we need to know about the standard deviation. So the PDF is standard deviation from the PDF is a very important information, because we need to do some preventive maintenance before considering this standard deviation, in order to avoid the risk to have some failure before to have the inspection. And of course, if you have random failure, we do not know, there's no any pattern or tendency of time to have some failure. We need to look on reliability, see when they achieve a lower level, that we have expected number of failure equal to 1, and before this time we implement some inspection and test. So that's why we are talking about, we are highlighting this type of index, and I suggest not use mean time between failure. Okay, here down we have all the inspections, downtime. The corrective maintenance downtime is very low related to the stator. we have the updated, we can see is almost 1,700 hours, and we have only 2.3 hours related to preventive maintenance, 0.9 related to visual inspection. And here we have the number of inspection of preventive maintenance, and in the end we have the total cost. We have an additional index, so that's the sensitivity analysis part. So the first one, the failure critical index, we already saw that we have a very small expected number of failure, but 100% of this failure is related to the stator. And then that shows that such equipment, that the preventive maintenance avoid the failures in other equipment. That's good, and the stator is the one that's the critical in terms of failure. If some failure happens, that will be caused by this stator. And considering the downtime critical index, we can see that the downtime caused by the traction motor is the most critical, 41% of total downtime. It's not too much, downtime is around 2.3 hours, but 41% of 3 hours is related to the bearing. On this downtime, we need also to clarify, to be sure what this downtime is about. And in the case of traction, motor, gearbox, reaction rod, and gear coupling are all about inspection and preventive maintenance. Okay, so here we get more clarification in this table. We have more detailed information concerning the index and the criticality concern each one of the equipment. So failure criticality 100% related to stators. We already discussion that. We can see that concerning the number of downtime. Here is considered not only the failures, that's very low, the expected number of failures, but also the inspection of preventive maintenance. So the bearing is the one that have more number of downtime, and consider the downtime, the number of shutdown, and consider the downtime. Also, the bearing is the one that have the highest percentage of downtime caused by preventive maintenance inspection. And then, of course, we can see all the operation availability. The one that have the lowest is very high, but have the lowest is the bearing. If you want to improve the operation availability, that's almost 100%. We need to improve the traction bearing. We need to be on mind that we also consider only 1,700 hours. If you consider the whole life cycle, we will see that such equipment is more critical, and then we need to assess something, make some assessment and to be sure that to be sure if we can improve or not, concerning the impact of life cycle cost and operation availability. And here are the operation availability without the inspection preventive maintenance. So we can see that we've got 100%. We've taken out all the inspections. There's no failure, but such inspection, of course, avoid all these failures that happen in this equipment. And then we have almost 100% as well to the stator. That's the equipment that have high reliability in 14,700 hours. Here, no expected failures for such equipment that we implement some tests and inspection and preventive maintenance, and the expected number of failure is for the stator is very low. And here the doing events, number of shutdown, that's each equipment is supposed to shut down the system. All this number of shutdowns here are related to inspection preventive maintenance, and here is the downtime rate with each one of these doing events. And then the block up hours here, we can see that most of them are close to 1,700 hours, what they expect. And then the number of corrective maintenance, of course, there's no corrective maintenance. The expected corrective maintenance that we can have is in the stator, but it's very low, close to zero. Then we move to the next result. Continuing with the result, we have the corrective maintenance downtime. Here is very low, considering the stator. We have the number of inspection. Here we see that we have a lot of inspection in gear coupling, gearboxing, and reaction rod. And here the related inspection downtime, so visual inspection. And here in the number of preventive maintenance. So we have only one in a rotor during these 14,700 years, 2 in gearbox, no in gear rods, and 23 in the traction motor bearing. So we expect to have a degradation in the bearing constantly, so we have some preventive maintenance on its schedule. So we carry out some inspection to check if there is some failures or bearing degraded, and replace and repair this degraded bearing. So we can see here the preventive downtime. So mostly is the tracking motor is the one that's more affect this downtime, and that's why the reason that this one is the equipment that leads the percentage of downtime, and this index in here, so in 41%. Okay, so no online condition implemented, so there's no downtime cost for that, as the system has no throughput production without inputting here. And then in the end we have the cost associated with each one of equipment, and then in the end we have total cost. So let's take a look on the software. Now. Here we have our RBD traction motor. So let's take a look inside the traction motor bearing. So this bearing, you know already how does it works by using the block sim. We have the tracking motor in here. That's like 100%. We have the normal PDF here for these hours, this mean and standard deviation. So we have corrective maintenance as well here defined. So that's the duration, 1 hour, the repair and replace of the bearing. We have a crew team here, and in the crew team, let's just click in here. Actually, I need to click in here, okay. And then we put the cost for S, that is 7,312. If we have corrective maintenance, so we need to remind, as long as we start to put this schedule maintenance here, 1, 2, and 1 inspection, we will not have any corrective maintenance, so this cost will not happen. But the other way around, we have the cost of each preventive maintenance inspection. So let's take a look. The first one is tracking bearing overhaul in 25,200. So that's after our time that we will model it, but of course that's one of the time that we want to check. The first time is the warranty period, 2 years. This is 14,700 hours, and after that, of course, we model for the whole life cycle. And then this maintenance policy will make sense. So here we have one team for this type of activities defined in here, and of course we have the cost for task. So it's for this overhaul is 742. We have another preventive maintenance, that's the lubrification. This one happens more frequently, in every 630 hours. We need to lubrify this bearing in the traction motor, so that takes 0.1 hours in mean and 0.01 average, so it's very fast. And here we have the cost per task that was included here. The further task is an inspection, so a visual inspection to just take a look on the bearing every 1,206 hours, so also very fast, the mean and standard deviation of such task duration. And we will have probably some cost associated with this inspection. Let's check. So there is no cost associated. That's a visual inspection, so personal cost was not included in here. Okay, so that is the traction motor. Let's take a look on the stator. The stator has no preventive maintenance. Here we have an exponential PDF. You can see that the failure rate is very high, and that's why we do not have any failure in this stator. So the rotor have also is different. We have a normal PDF with 2 million hours, standard deviation 50, and we have 1 preventive maintenance here for the rotor. We including 8,000 hours. We carry out some preventive, some schedule maintenance, and they have the cost of 500 euros for this schedule. We expect to get some failure in there. The gear coupling, is also important equipment for the traction motor. Here we have the normal PDF, so we have the mean and standard deviation. We have the duration of the task in here. For this equipment we have by 2 hours. So here just highlight that we use this repair time for other equipment. That we have actually this system was carried out for a real propulsion system, so we have a lot of information. I got that from an equipment, but that's not influence on the model. So the gear coupling have a lot of preventive maintenance, so we need the first one is the renew oil in every 18,900. So after this 14,700 hours that we planned. So the second one is the renewal of the gear coupling is 147,000 hours. It's around 20 years. So we have some inspection as well. We have the first inspection policy, so that's a visual inspection every 630 hours. And here in this inspection, let's take a look if we have we have a task duration. Here there's some times that affect such item here. Then we have additional inspection. On the finding here also 606 hours. So checking the screws. So there another inspection, visual inspection to check the screws. Okay, so the gearbox is the next one. We have this value for normal and standard deviation very high in terms of hours, but we have a lot of preventive maintenance here. The first one is the overhaul. So we have 30,500 hours the overhaul. So the gearbox is in 2 hours repaired, and then we have a crew to carry out the overhaul. Probably here we do not have any cost associated here, but we put in here cost per task 400 euros. So that is the overhaul. We have the exchange time, and then you can, it's an important point, in 31,500 hours. So here is the time to carry out such scheduled maintenance. And there is no let's take a look on if there is some associated cost in here. No, there's no associating cost in this case. Probably it's already accounting another in this one overhaul. And the next one is a renew oil, checked fuel and drain. So in every 5,040 hours, that is accounts very fast to carry out this activity. And we have a cost task for this activity that's 24 euros. So examine the oil inspection. So we have every 630 hours oil inspection. There's no associated cost in that. Yeah. And we have additional inspection of oil. So examine oil thicknesses, so it's more precise type of test, and it's the same range of time. So that's release all the activities, examine for damage in 45,040 hours. And again, as is also including the cost that we have other activities this time. So a lot of preventive maintenance session for the gearbox. Then for the reaction rods, what we have also some high mean and standard deviation for a failure, and we have some 3 hours for the repair. And here we have 3 preventive maintenance. So we have the overhaul in 31,500 hours after the time defining here. So probably we have some costs associated with the overhaul. We do not include in here, so let's just take a look on here. That's 25 euros the cost of this overhaul. And yeah, again, another exchanging, another test that we have in the overhaul. So here we did not put the cost because already including overhaul. So it's very important also to understand when we have activities with the same period of time. So we have such priority here, and this priority will define which one will be carried out if they have same activity in the same time. Okay, so for example, if we have the overhaul, the overhaul will also include the exchange and so on. And here we have one inspection, define it. So inspection every 630 hours, and we did not put any cost to visual inspection in the loading cost. So here I think that's the graph. That's one schedule maintenance that we have for the rotor. We can see all this inspection in every 630 hours that we have here, and then of course some overhauls or exchanging here, and for status no preventive maintenance. And then we need to come in here and run the simulation. So again, let's just remind the concept. We need to put the number of simulation we calculate in hours, so that is our 14,700 hours. Now we are running the simulation. Here up we can see the value of the mean operation availability. That's the average of each result of the total number of simulation. We can see also that's when going after the 200 it's starting to be smooth to this value. Now we can check the details, and then similar that we've got the operation availability without any intervention, reliability, expected number of failure, all the results that we've got. We also have these results, the point results along the times in hour for this 14,700 hours. So we have the operation availability, the reliability, how it's decreased, as well as the total cost, how it was calculated, the mean operation availability, the availability, the expected number of failures. And here we have some information about system cost. In the end, how you get this 571 the total cost. So that's something as related to preventive maintenance here, and that we need to find out. So of course we already demonstrate that in the blocks results. So here are the blocks results, where we've got these two templates that we have in our slides. Here is the complete template with all the information. We just divide by 2 to have this information. And here we have block cost, another type of results that we can demonstrate the total cost for each one of equipment, and where this cost is related to preventive maintenance, for example, in the case of all this such components, as we can see here. So it's in pounds, not in euros. Yeah, and what is also interesting here we have the block details. So you can, if you want to look on a stator, all the information about the stators, the performance index, the criticality, the number of events, and so on, the cost. We can look on by each equipment, the spare part with the fan spare parts, the simulation summary. So here just demonstrate the end time, how long does it take, how number of simulations, and what is the most important here is the rank. That's the summary that we have. So in terms of failure criticality index, the status, the one that's more critical. In terms of downtime critical index, the traction barrier is the one that's more responsible for downtime. Block availability rank, you can see in the bottom, is the traction motor bearing. Because of that, if I want to improve the traction motor operation availability, I need to start with the traction motor bearing, after improve the gearbox, and going up to each one of such equipment. Here's the failure modes, very low number, expected number of failures. We can see here number of downtime time. So we need to be clear that most of this downtime time is caused by preventive maintenance. So here we have different other blocks related to other information. So those are the most relevance information that we have, we can see that we can got different information. Here we have the plots. So that's the free failure criticality index. We also demonstrate that during the presentation, and that's one of the graph. The other one is doing downtime critical index. So that shows the tractor motor is 41%. We can click in here and automatically see how much percent each one impacts. And of course, if I want to have other type of index here, I just click on here. That will automatically provide such index. So now we've got the end to this model. So the objective was to give a first introduction how to carry out run analysis and equipment level concerning the components of such equipment level. So we demonstrated tractor motors. In tractor motor, that we consider the failure class A that shut down the tractor motor, so the most critical equipment. And in this case, we saw that there are mechanical equipment and also electrical equipment such as stators. So in this case, we did not apply any preventive maintenance, but we are lucky that such equipment we expect to have a low expect number of failure in the period that we demonstrate. But of course, during the life cycle, that failure will happen, and we always need to define some test time based on the reliability and expect number of failure to decide the time that we test such equipment. So in general, we have these characteristics when we're modeling train systems. So we have different equipment. Some of them have only electronic components. Others have only mechanical, and some of them combination of both. We need to be careful what we are inputting in as information, as inspection and preventive maintenance. And in the end, we get this result. So that's a very good solution software that's enabled not only to get the main targets such as operation availability and reliability, but as well as expect number of failure to carry out and implement a life cycle cost prediction, and in addition to give the critical analysis. So we had a chance to see the operation availability rank and the failure critical index and rank and the number of failure rank considering all the components, and that gives a very good idea of what kind of equipment needs to be improved first. So that is the idea of sensitivity analysis. And then of course, if we need to carry out some that was the idea of criticality analysis. And if you want to carry out some sensitive analysis, we can go further and model different configuration of our system, put different preventive maintenance policies, and test that, and also test the impact of other systems in our equipment. So thanks a lot for your attention. If you have some question about this model, just send us an email. It will be my pleasure to answer you. So let's move to the next model. The next model will be the last model of this training, and we'll demonstrate how we model the main critical system for railway trains, such and locomotive as well, such as in the case of trains, pantograph, brakes, and bogies, and we also have the bogie and the brakes in a locomotive. So those are the critical system. We take a look in details how we model that, and then in the end you have the full understanding about the run analysis.